Okay, ladies and gentlemen, here you have the video for multi-compartmental kinetics assignment. As today I was showing that the major equation for this calculation related to multi-compartment model is this one. C is equal to a e to the negative alpha t plus b to the negative beta t. So always before you do this calculation, one concept you have to keep clear is that here we have two curves. This is the slope, negative alpha is the slope of this curve, and beta is the slope of the elimination phase. This is distribution phase, elimination phase. So here is question asking to calculate the terminal half-life. That means question is asking to calculate this half-life. So to calculate this half-life, we have to use this equation. T half is equal to T half beta. T half beta is equal to 0.693 divided by beta is equal to 0.693 divided by 0.0204, which is going to be your 33.97 hour. So this terminal half-life is 33. This answer is 33.97 hour. So this is going to be your answer. And then asking for terminal distribution half-life. When we talk about distribution, that means we have to use this number. So that means we have to use T half alpha 0.693 divided by alpha. Our alpha is 0.419 is equal to 1.65 hour. So this is our would be 1.65 hour would be our distribution half-life. So that means if you think about this is your curve, your alpha is equal to 1 point alpha t half. This is t half, sorry. T half for this curve is 1.65 hour, and T half for this part is equal to 33.97 hour. So this is the two answers. So now it is asking for plasma concentration at 1.6 hour. Plasma concentration at 1.6 hour. To calculate, use C is equal to A e to the negative alpha t plus b e to the negative beta t. Now we have to calculate 1.6 hour will be 9.04 times e to the negative 0.419 times 1.6 plus 2.52 e to the negative 0.0204 times 1.6. This will give you something 7.06 milligram per liter. So this would be your answer for, here is the calculation, this would be your answer for 7.06 milligram per liter would be your plasma concentration at 1.6 hour. And then, so this is your answer, one of the answer. So let's clean those. This answer we'll need later, so we have to keep them. And then plasma concentration at 0 time. So again, C, we have to calculate C0. C0 is equal to A e to the negative alpha times 0 plus B times E negative beta times 0 times 0. So C0, this part would be what? Is equal to 1. Is equal to 1. So C0 is equal to A plus C0 is equal to A plus B. That means C0 is equal to A plus B. We will have 9.04 plus 2.52. So to make things easy, so always you remember C0 is equal to this. This is your C0. A plus B. Do not have to do this all the calculation as I was trying to show you. So this is, just a minute, someone is calling. Sorry guys, this is one of the problem when I videotape from my office. It's always calling. So here what I was talking about, that you calculate your C0 easily without going through this long process. And it says, remember, this equation will not be in the equation sheet, you just remember that. And then plasma concentration at C0 would be your 11.56 milligram per liter. So let's put this here. We will need this concentration again. Now apparent volume of the central compartment. Central compartment, as you remember in I think first few lectures, someone has to say volume distribution. The equation for volume distribution is this. Equation for volume distribution is this. Volume distribution is equal to dose, amount of the drug in the body, and the concentration of the drug. And I think I did not teach this part. Here, if you remember the solution, here you know the fixed amount of drug you have added, and then you collect sample. If you know the concentration, so you can calculate always volume. So calculate the, so from the, you have the amount and the concentration, you can calculate. Same way we can calculate volume of the central compartment. So and volume of the central compartment, we calculate VC. We calculate how? Dose by C0. And what is our C0? Well, our C0 we have calculated. Our C0 is this one. And our dose I think is 110 milligram. So our dose is 110 milligram and C0 is 11.56 milligram per liter. So here is your VC is going to be 9.52 liter. So 9 point volume of the apparent central compartment, it is here. Your central compartment is 9.52 liter. So again I am marking those. It's annoying that every time I have to do this. I wish I could do it with the pen. So and then total plasma AUC. If you remember AUC, in one equation we had AUC we had AUC is equal to C0 by K. If you remember this equation, let's go back to the equation sheet. So here you go. This is our equation. You see, this is our equation. So in this way you calculate AUC. So how you calculate AUC? In our case we have two K's and we have two C0, so we have to do AUC is equal to A by alpha plus B by beta. So we have to calculate, as we know, AUC. A is 9.04 divided by 0.419. Let's see if it's 0.419. Yes, 0.419 plus B is equal to 2.52 divided by 0.0204, and it comes as apparently 145.110 milligram hour per liter. So here our AUC is 145.10 milligram hour per liter. Again I am marking those. We'll make this later. Now clearance. To calculate clearance, if you remember again that equation, if we go back to the always equation sheet, try to find out clearance. One of the equation is this one. You can calculate clearance by from this equation and from that equation. So now to calculate clearance, we will using dose and AUC, we will use clearance. More fancy I want to do, more complex here. Now CL is equal to dose by AUC. So we know our dose is 110 milligram and our AUC is 145.1 milligram hour per liter, and then our CL is going to be 0.76 liter per hour. So this is our clearance. Our clearance is 0.76 liter per hour. And then volume distribution in the terminal phase. Volume distribution in the terminal phase, again the same simple calculation we have to do. If you go back to that equation sheet again, that equation sheet, this is the equation we are going to use. Let's see, this is the equation. Let's clean it. Here, this is the equation we are going to use to calculate volume distribution of the terminal phase. So for terminal phase B, V beta is equal to CL by beta. So here we have 0.76 divided by 0.0204 is equal to 37.16 liter. So our volume distribution of the terminal phase is 37. Volume distribution for terminal phase is 37.16 liter. So let's mark this because we need this later. And the time to reach 90% of pseudo equilibrium. Time to reach, if you remember, this is our distribution. And just to recall, let's go over the distribution, pseudo distribution. This is our assume this is our curve, and this is the pseudo distribution phase. Time to arrive, this is called pseudo equilibrium or distribution equilibrium. And we know half-life of this distribution is this 1.65 hour. So always, you know that at T 90% is always 3 half-life, so that means we calculate T 90% is equal to 1.65 times 3.3 would be 5.46 hour. So this is the time we'll need for pseudo distribution. This is your pseudo distribution time. Now we have some other calculation. I will finish this today so that we do not have to post another video. Now it is asking for percent estimation, percent degree of error of AUC associated an assumption of one compartmental model. One thing I have not yet covered in the class. Let's go over this material a little bit. As you can see here, if we assume, let's forget about, we do not consider this distribution phase. As I have been explaining to you that we have two phases. We have two phases. Distribution and then, so what some can erroneously do, or if you are not familiar with the kinetics of the drug, you assume it is one compartment model. In that case, what do? You just take a line in between people, or you just use this distribution. You do not elimination phase, you just use this part, you just use the information of that beta phase or terminal phase. So if you use all the assuming that it is a straight line like this, then it will give you certain error. Okay, so for example, what we have done in case of correct AUC, we have done AUC. You see, if you remember AUC, we have done AUC is equal to A by alpha plus B by beta. But one person may assume, or who has no clue about the kinetics of the drug, which happens, say, if it's a brand new drug, there is no literature. It is one compartment, two compartment. Fortunately, most of the drug follows one compartment model. So assume there is one of the drug, one of the very important drug, digoxin. I used to say digoxin, but I know that this perhaps hard. Digoxin shows two compartment kinetics. So for this reason, you assume that you did not take into consideration this distribution phase. You are calculating everything based on that elimination phase. So then that will give you inaccurate AUC, inaccurate volume distribution. If you remember how we calculated VC earlier, we have calculated volume centered dose by A plus V. So instead of doing, you calculate my volume like this, dose by B. So if you calculate dose by B, then it will also give you incorrect volume distribution. So let's go back to the assignment now. So we can see, if we use this equation, I will explain this thing in the preview video and also on Thursday's class. As I have mentioned, the correct one would be what? AUC is equal to A by alpha plus B by beta. What you are doing, and VC is dose by A plus B. This is the correct one. We are considering both phases. We are considering both distribution and elimination. So for some reason, whoever is a new drug or new pharmacist or whatever, so you do this calculation, AUC is equal to B by beta. I don't know what's going on today. B by beta, AUC is equal to B by beta, and VC use dose by B. This would be your incorrect AUC. Incorrect. That's why you say AUC incorrect. So in the note you will see it's called AUC incorrect and BC incorrect. I hope you got it. Why is incorrect? Because the correct, if the drug really shows two compartmental model, your AUC, correct AUC is this one. Ladies and gentlemen, correct volume distribution will be this one. You consider both phases, elimination, distribution, but if you are not familiar with this, you use only the elimination phase, you will get incorrect AUC, incorrect volume distribution. So if you get this incorrect volume distribution, there is a formula to calculate this incorrect volume distribution. So first let's calculate incorrect. What would be the incorrect AUC? Here incorrect AUC would be AUC incorrect AUC incorrect would be B by beta. That means you are not considering your distribution phase. So B would be 2.52. I guess this is 2.52. Yes. And your beta is 1, 2, 3 point. No, sorry. Your beta would be 0.0204. So in that case, I think it would be 123.53. Let's see, I think it's 123, incorrect. So now this is your incorrect IUC. So there is a percent error. Calculate the percent error. The formula for the incorrect IUC is just AIUC correct. I don't think it is in the equation sheet. You have to remember AIUC, AIUC incorrect. This is AIUC incorrect. And AIUC correct divided by AIUC correct and multiplied by 100. This is the equation to calculate percent error. Calculate percent error when you consider only the elimination phase. You do not take into consideration distribution phase. So in your case it would be 123.53 minus AIUC correct was what? I think this was the AIUC correct. So 123 and 145.10 divided by 145.10 times 100. 50 here will be 14.87. So you see, if you do not take into consideration distribution phase, there will be error in AIUC would be 14, almost 15%. So, and the question is asking you absolute degree of estimation of AIUC. So, see, estimation of AIUC, assumption of one compartment, that only the points that best fit through the terminal phase instead of actual. So, in that case, you will have about 15% error if you use this assumption. Now, volume of distribution, again same. In volume of distribution, incorrect would be what? VC incorrect would be dose by B. So correct one is what? Remember, dose by A plus B. So but instead of you do not consider A, you are using best fit. That means instead of using both into consideration, you just did that. Boom. So then that will give you incorrect volume of distribution. So what is going to happen? Your incorrect volume distribution, 110 divided by 2.52 is going to 43.65 liter. So this would be your incorrect volume distribution. So percent error. V incorrect and VC correct, again VC correct. So we know that our incorrect is 43.65 minus, if you go back to the volume distribution, our correct volume distribution is this one. So 9.52 divided by 9.52 times 100. Your volume error would be 355.70%. Can you believe it? So this would be your error, percent error. So here, if you use that volume only B, like dose by B, your percent error will be about 358.73%. So that means you should know the drugs kinetics, one compartment or two compartment model. So so these are all calculation. We have now two concept question. Why is important to consider distribution phase in the calculation? You know that. It will give you incorrect volume distribution. Its clearance will be underestimated if not considered. Volume will be overestimated. As you can see here, you see our volume distribution is 43 and our actual is 9 points. So volume distribution will be overestimated. And when volume distribution is overestimated, what happens? If you remember the equation, this equation, if you this is the equation for CL is equal to KV. Now you want to calculate CL, you have K, so you have big V, means larger volume distribution, you will have also larger clearance. So that means this is not correct. Our correct answer is this one. So this is not correct because both clearance and volume distribution will be overestimated. Here in the note, I guess somewhere I wrote this here. Ladies and gentlemen, here it is written. So if we use this, the volume of distribution will be inflated, that means overestimated, because you disregard the initial phase. And use the smaller AUC, clearance will also be inflated. So this is the answer for that question. And then, so this is answer question. The site of action is associated with the tissue compartment. Does the plasma concentration obtained at 1.6 hour will give useful information with regard to the effects of the drug? Okay, here I will explain this thing in previous video too. You have to remember one concept. So as you can see, this is the distribution phase, that means it is central compartment. Here you have the peripheral compartment. So this drug has the sample and you remember the equilibrium is achieved. Yeah, this is the one. It comes to this point after 5.46 hours. But you have taken a sample at 1.6 hours. Okay. But the drug works. You see, the action is in the tissue compartment. But drug works in this area at this concentration. So that means if you take sample at 1.6 hour, is not going to give information if it is drug is effective or not, because you are taking sample before even the distribution equilibrium has come. So you are taking all the samples during the distribution phase. Sample needs to be taken at the terminal phase because drug is acting on the central compartment. So the site of is going to no. Your answer is no. Answer is no because pseudo equilibrium has not achieved in 1.6 hour. If you have taken sample at, for example, at 6 hour, yes, but you have taken sample before the equilibrium has come, before equilibrium, that's why this is not going to give you information about the concentration of the drug at the site of action, because site of action is the peripheral compartment. I will explain all this again in preview video. There will be a short preview video, so I will try to explain again. And sorry for the interruption. One time my wife called, one time my boss called, one time my graduate student. It was annoying, but although I put note on my door, but no knock, but I cannot stop the phone call. I'm sorry for this interruption, but I hope this helps. Thank you.